Penso di sì. Le versioni ci stanno, almeno sembra.
Sto registrando ormai.
Ok.
Should I start?
Yes.
Okay. So in this lecture 6, I'm going to explain a variational approach in order to solve certain complex Monge-Ampère equations. So x omega is a compact manifold of complex dimension n. V denotes as before the volume of x with respect to omega. And MA of phi is the normalized Monge-Ampère, complex Monge-Ampère measures of the potential phi. And I would like to solve the following complex Monge-Ampère equation. Monge-Ampère of phi is equal to e to the minus lambda phi times mu. And I focus on these particular complex Monge-Ampère equations because, as you will realize on Thursday, these are precisely the complex Monge-Ampère equations that show up when one tries to construct a Kähler-Einstein matrix. And here today, I would like to explain how to solve these equations by means of a variational approach. And let me start immediately by discussing or defining the appropriate functionals that will play a central role in the sequence. Namely, you look at f lambda with to a Kähler potential phi associate E of phi. So there are two components. The first term is the energy functional that we have been discussing in the previous lecture, plus 1 divided by lambda log of the integral of e to the minus lambda phi d mu, and the integral is over x. So it is understood here that for lambda equal to 0, you can recover the 0 case by passing to the limit as the parameter lambda goes to 0. And if you do that, then what you get is e of phi minus the integral of phi against d mu. Let me start by making the following simple observation, that since we assume here that mu is a probability measure, these functionals are invariant under translation. So when dealing with these functionals, you can think of them as acting rather on omega phi rather than on phi, or you can think of them as acting on normalized potential, if you like. Okay? So the idea, and this is what I'm going to justify, is that the solutions of the Monge-Ampère equation that we are interested in are actually the critical points of these functionals f lambda. And I should say right away that in the calculus of variation, half of the hard work is to identify the appropriate functional. So it's a classical idea to try and solve nonlinear PDEs by extremizing certain functionals. But there are, for a given nonlinear PDE, there are many, very many, infinitely many possible functionals that you can consider. And a very difficult task is to identify ones that you can indeed control and work with. And in that way, I'm already out of the blue giving you the appropriate functional, so somehow cheating a bit. But this is due to the fact that there have been several attempts in the past, especially in the 80s, by Aubin, by Calabi, by Yao, by many others. And it's only, I guess, in the 90s that these functionals f lambda appear to be the right one to consider. So let me skip that part of the history and focus on the detailed explanation of why these are the right functionals. So the first important property of this functional lies within the following statement, namely, if you differentiate a path of scalar potentials along f acting along a path of scalar potential, then what you get is the integral of phi t dot Monge-Ampère of phi t. So this, we have made the computation in the previous lecture. This is simply the differential of the E component. And then if you differentiate the log term, what you get is minus the integral of phi t dot e to the minus lambda phi t mu divided by the integral of e to the minus phi t d mu. So you can make the computation for lambda different than 0 and then pass to the limit, or treat lambda equals to 0 as a special case, for which actually the computation is even simpler. But this is what you get. And in particular, so this is a straightforward computation. The most difficult part is the differentiation of the E part, but this we have done in the previous lecture. So in particular, if you consider phi t, which is phi plus tv, where v, say, is a C2 smooth guy, then you see that phi is critical for f. That corresponds to the fact that Monge-Ampère of phi, so you look at that, say, at t equals to 0, and what you end up with is that the Monge-Ampère of phi should be equal to e to the minus lambda phi mu divided by integral to the minus lambda phi d mu. And this is equivalent to the fact that Monge-Ampère of phi tilde is equal to e to the minus lambda phi tilde mu, where phi tilde is simply phi plus an appropriate constant. Okay? So you see that this is the first good sign that these functionals will possibly do the job for us, namely the Monge-Ampère equations that we are interested in are the Euler-Lagrange equation of this functional. Let me, however, make an important remark here, is that this is okay, or this makes sense, if phi plus tv belongs to at least the set of omega prosomanic function. And this requires omega phi to be strictly positive. So in other words, there are two ways to think of the computation that I've just done. Either you are working in the smooth world, and then there's no problem. Phi is smooth. Omega phi is a smooth scalar potential, so omega phi is a scalar form. And then if you perturb it a bit, phi by adding a small contribution like TV, then you stay, you remain a scalar potential, and then everything that I've done is okay. But in the sequel, we are going to work with less regularity, because in a certain sense, if you allow for less regularity, then you gain in compactness. Hence, you have more tools to make the analysis, but then there will be this issue to be dealt with, okay? So we cannot expect with less regularity to have this positivity information. And towards the end of the lecture, I will explain how to resolve this difficulty. But for the time being, let me simply say that the first step is that we have certain functionals, and that the Euler-Lagrange of these functionals are the Monge-Ampère equations we are trying to solve. So what is the strategy for solving this equation? So first, we are going to show that f lambda is upper semi-continuous on the class E1, are well defined and upper semi-continuous on the class E1. Secondly, we are going to show that f lambda is proper when acting on E1, at least when either lambda is non-positive or lambda is positive but small. I will make this how small more precise in the sequel. Then we know that E1C is compact. So we are going to consider the supremum of f lambda on E1 and trying to say that this is reached, this is actually a maximum, so this is reached by a certain guy phi. And finally, we are going to resolve the difficulty that I was mentioning. We are going to explain that this phi is a critical point, hence a solution to the complex Monge-Ampère equation. And one could also wonder whether this is the unique solution. So there is a fifth piece of information that I'm going to briefly discuss, which is that f lambda has the tendency to be concave. And this is connected to the fact that there is a unique solution. The picture you can keep in mind is the following. We have a guy like this, and we are going to consider this guy here. And obviously, in one real dimension, at this point, the differential is 0. We have a critical point, which is a maximizer, and this yields a solution of our equation. Okay? The slight problem is that we're actually working with a functional acting on an infinite dimensional space. Moreover, the concavity is not so strict and not so obvious. And finally, we are working actually on a cone and not on an open set. So it's difficult to move around here. And this is this point 4 that I'm going to solve by the end of the lecture. Okay, so that's actually the rough plan. And let's see with more details what is indeed working. So let me start by the upper semi-continuity property. And the proposition is like this. F lambda is upper semi-continuous if lambda is non-positive. It is delicate to understand the upper semi-continuity property for lambda being positive, but nevertheless, f lambda is upper semi-continuous on a subclass E1C if lambda is positive. So maybe not on all of E1, but at least on a compact subset of E1 that we have discussed in the previous lecture. Here is the proof. So let me recall that f lambda of phi is E of phi plus 1 divided by lambda log of the integral of e to the minus lambda phi d mu. And let me start by saying that this functional is indeed well defined on E1. Why is that so? Well, the first part, the E functional, is well defined exactly on E1. That's sort of the definition of E1, that this guy makes sense. And then what you end up with is you have a probability measure and you try and integrate e to the minus lambda phi. Either lambda is negative, that's the easy case. Then you are integrating a bounded function if lambda is negative, or you are integrating phi against mu if lambda is 0. And because mu is reasonably nice, this type of integral is finite. More delicate is the case where lambda is positive. Then you are integrating e to the minus lambda phi against mu, and this starts to resemble Skoda's integrability theorem. And when mu is in LP with respect to Lebesgue, then we have seen in the previous lecture that in E1, because we have 0 Laurent number, all these integrals are finite, whatever large is lambda. Okay, so it's okay by Skoda theorem for lambda positive and for simpler reason for the other cases. Okay? So assume now that phi j converge in L1 towards phi, and everybody lies in E1. We can assume, extracting and relabeling if necessary, that phi j of x converges towards phi of x almost everywhere. Okay? And then let me use Hölder inequality. What I do get is that the integral of phi j minus phi. So let me treat first maybe the case lambda is equal to 0 first. So you see that this quantity against the mu by Hölder inequality, and let me recall that mu is f dv with f in LP. So this is less than f LP times phi j minus phi LQ of dv. And this goes to 0 because LQ and L1 topology are equivalent for pseudo-harmonic functions. So this implies that f0 of phi j minus f0 of phi, which is e of phi j minus e of phi, plus integral, oh sorry, minus integral of phi j minus phi d mu. So this goes to 0. And this piece here is upper semi-continuous. This was explained in lecture 5. So this tells you that F0 is upper semi-continuous. Okay? So that's for F0. Let me maybe here explain lambda less than 0. Well, this is the same argument. because integral of e to the, let me maybe rather the negative case, I will actually only treat the case lambda is -1, and the positive case, I will treat the case lambda is +1 in order to simplify notation. So here, my claim is integral of e to the phi j d mu converges towards e to the phi d mu. And this is even simpler because here, the functions e to the phi j are quasi-PSH and bounded. The fact that you have an exponential with this nice sign allows you to actually deal with bounded prosymmetric function. So same argument and even simpler. So let me now say one word about the case, the difficult case where lambda is positive. And let me treat lambda is +1. So the claim is that the map phi goes to integral of e to the minus phi d mu. I cannot say that it is upper semi-continuous or that it is continuous in E1, but it is continuous on E1C. And the proof is similar to what I just wrote, modulo small detail, namely, I will use the fact that if A, B are positive, then e to the A minus e to the B is certainly less than A minus B times e to the A plus B. And I use that with A, which is minus phi j of x, and B, which is minus phi of x. Then you obtain that integral of minus phi j minus e to the minus phi d mu. I want to say that this goes to 0. Let me maybe, I will use first Hölder. So let me replace A by Q phi j and B by Q phi minus phi. So by Hölder, because mu is f dv, this is less than f lp. No, sorry. Let me first, this will be more comprehensible, I hope. Let me first use my inequality star and say this is less than phi j minus phi of x e to the minus phi j of x minus phi of x d mu. And then use Hölder to say that this is less than what? Then f lp, and then integral of phi j minus phi q e to the minus q phi j minus q phi of x d mu, dv, sorry. And maybe use a Cauchy-Schwarz to say this is less than FLP times, sorry, and this is to the power 1 over q. And then this will give me phi j minus phi L2q, and then integral of e to the minus 2q phi j plus phi dv to the power 1 divided by 2q. Well, in the end, what do we get? Here, this goes to 0 because L2q and L1 topology are equivalent for PSH functions. And this is uniformly bounded by Skoda uniform integrability theorem that I mentioned earlier, because we are working in E1 Cx omega. So this guy is compact. You are away from positive Lalong numbers. So these guys are uniformly controlled as J moves. And in the end, you see that the continuity of this difficult integral is actually a consequence again of L1 convergence plus Coda's uniform integrability. Okay? So this shows that the functional f lambda is continuous because f lambda is upper semi-continuous because f lambda is given like this with this part which is continuous when restricted to appropriate subsets, and this one, and this one is upper semi-continuous. Okay, so that's the first step in the variational approach. So let me move on to the second property, which is the properness of the functionals. Let me start maybe with the simplest case, which is say lambda is -1, and the same argument treats any of the cases where lambda is negative. So my claim is that f -1, so it's a lemma if you like, f -1 of phi is less than E of phi minus the supremum of phi plus a certain constant, C mu. And this means, this is the properness property that I want. And what it means concretely is that f -1 of phi goes to -infinity as E of phi goes to -infinity. So E of phi, you can think of it as a kind of norm, or at least for normalized functions in E1. And what you want to say is that when you want, what we want for the sequence is that when we are going to try to maximize f lambda, we want to maximize on compact subsets of E1. So we want to stay in a finite level sets of energy. And this is the reason for considering this properness property. If as the energy goes to -infinity, the functional goes to -infinity, then when we are going to try and extremize f lambda, there is no need to look at, we can restrict to finite energy levels. Okay, so why is this lemma true? Well, simply because you see that f -1 of phi is E to the phi minus supremum of phi plus, sorry, it's a minus maybe. Yeah, it's a minus log of integral of E to the phi. Oh, let me not skip one step. So by definition, it's minus log of integral of E to the phi d mu. So that's the very definition. And then in the integral, I replace phi by phi minus sup plus sup, supremum. So I get E to the phi minus supremum of phi minus log of integral of E to the phi minus supremum of phi. Okay? And now I claim that, where am I? It was like this. I claim that this quantity here is obviously less than 1, because phi minus supremum is less than 0, the exponential is less than 1, and you take your average with respect to a probability measure. And I claim that this is bounded from below by a uniform positive constant, delta mu, say. And this is because the set of functions which are subnormalized is compact. When you take the exponential, you get a bounded function which is away from 0, which is not identically 0 because phi is not identically minus infinity, and therefore the integral has to be strictly positive. I'm maybe too quick here, but it is a really simple compactness argument here to get strict positivity. And as a consequence, because of the minus sign here, you get that this is less than e of phi minus supremum of phi minus the logarithm of delta mu. Okay? So this is it for lambda minus 1. And I'm not using much, actually, much property of the measure mu. So it would work for those who would be interested in this extension. This argument would work for mu, which is very general. And the only property I need is that the measure does not charge polypolar sets. Okay, let me treat now the case lambda is equal to 0. And here again, the lemma is like this. That f0 of phi, which is e of phi minus the integral of phi d mu. Well, this quantity, you see, is e of phi minus supremum of phi minus integral of phi minus supremum of phi d mu. And I claim that this is less than e of phi minus supremum of phi plus a constant c mu. And the reason lies here. This quantity, this is the L1 norm of subnormalized function with respect to mu. And this is controlled by uniform constant because PSH is in L1 of mu if mu is FDV with F in LP. And this is, I'm not going to give more details today, but this is something we have encountered in lecture 4 last Thursday. And I spent some time describing this uniform integrability of such measures. Okay, so it's, once again, one could actually deal with more general measures. And actually, so let me just add a remark here. So properness is again true here for measure mu, which are more general. And the only thing you need to know is that E1 is in L1 of mu. If you know that, then you obtain a properness property, which is slightly more involved than the one I just stated, but which is nevertheless true. And that's somehow one reason why one can solve Monge-Ampère equation, the flat case, so for lambda equals 0, for measures which have this property that E1 is in L1 of mu. But I don't want to make things more confused today, so I rather stick to the case of absolutely continuous measures. And let me finally discuss the case where lambda is positive. And first, by saying that f lambda is not necessarily proper. So it's not always the case that f lambda is proper when lambda is positive. And a simple example is when x is P2, the complex projective plane, lambda is 1, omega, sorry, not P2. Sorry about that. Assume x is the blow-up of P2 at one point. And assume that omega is a Kähler form in the first Chern class of X. Then F1 is not proper. It's not totally obvious to check directly, but it's doable. But it's clear that it's not proper for another reason, which is more theoretical, is that if F1 would be proper, then as we will see with the sequel of the lecture, we would be able to solve the corresponding complex Montgelas equation. But then this would provide a Kähler-Einstein metric on P2 blown up at one point, and it is known that there are no such Kähler-Einstein metric in that case. So this will become more understandable Thursday, because in the first lecture on Thursday, I will describe the connection between Kähler-Einstein metric and solving such complex Montgelas equation. So this is a negative result here, and this is an important warning that the case of lambda positive is indeed much more complicated. And here is a small positive result, which is that if lambda is positive but not too big, and how small should it be? It should be smaller than Q. Q being the conjugate exponent of P. Remember that mu is f dv with f in NP, times the uniform integrability exponent in Skoda's theorem with respect to the class omega. So if lambda is that small, then f lambda is proper. And the proof is actually simple. It's simply that if you look at integral of e to the minus lambda phi d mu, let me write it like this. Phi minus sup phi d mu. Then by Hölder, this is less than fp times integral of e to the minus q lambda phi minus sup phi dv to the power 1 divided by q. And this is less than a certain uniform constant by Skoda. So here I'm allowing the functions to have Lelong numbers, but as we discussed 1 week ago in lecture 2, the Lelong numbers cannot be too large. Hence, the uniform version of Skoda's theorem tells you that if lambda is small enough, then Q lambda is small enough, and then these quantities are under control. And in the end of the day, this tells you that f lambda in that case is again bounded from above by e of phi minus sup phi plus a uniform constant. Okay? So to summarize, these functionals are always proper if lambda is non-positive. They are proper if lambda is positive but rather small. And if lambda is larger, then it depends. And you need to make a much finer study of the geometry in order to understand when or if possibly there are or not so proper. Okay? So properness is an important issue when solving this equation with lambda positive. Okay, so I would like now to say a few words about, I guess it's part 4, about concavity. And again, I will discuss things depending on the sign of lambda. Maybe the simplest case is when lambda is 0, or the most obvious case. Well, then we know that phi goes to E of phi. In any case, we know that this is affine. This is concave along Euclidean segment. We have discussed that in the previous lecture. And on the other hand, you see that phi goes to integral of phi d mu. This is affine. So if you put the two things together, you get that phi goes to f0 of phi is concave along Euclidean segments. Okay? What about the case lambda negative? Well, you can use Hölder inequality to check that phi goes to the integral of e to the minus lambda phi d mu is convex along Euclidean segment. And therefore, when you take, the log of that is convex. Maybe it's probably disturbing to treat the general case because you don't see the sign. So let me treat the case lambda is equal to -1. And then I hope it will be a bit clearer that what you are dealing with is exponential of plus phi d mu. And I'm just saying that a simple application of Hölder inequality tells you that this function is convex. But f minus 1 of phi is e of phi minus this logarithm. So this is concave. This is concave with the minus sign. So this is concave. Okay? So for lambda equals 0, f0 is the sum of a concave functional and an affine functional. For lambda negative, f lambda is the sum of two concave functionals. So it's even more concave. And it helps again in getting uniqueness, if you like. And then for lambda positive, say lambda is +1, then the same Hölder inequality tells you that f1 is concave plus convex. Now it's the same story. Hölder inequality will tell you something, but it goes the reverse direction. So what do you get? Who knows? But actually, there is at least a special case, and this is a very important theorem by Berndson, which says that if x is Fano, that is to say the first Chern class of x is positive, and if omega lies within this first Chern class, then t goes to e of phi t. Let me phrase it differently. then t goes to log of the integral of e to the minus phi t d mu, then this is concave along not Euclidean segments, but along Mabuchi segments, or Mabuchi geodesics. While, and this is not a theorem of Berndson, but this is a much simpler property, t goes to e of phi t will be affine. And the conclusion is that F1 is concave. So I'm not going to explain this today. And actually, I will simply recall it in lecture 8 Thursday. But there is another type of geometry which somehow helps to resolve this indeterminacy. You have concave plus convex along Euclidean segments. And we will briefly introduce Thursday another geometry, which is the Mabuchi geometry, where concave becomes affine, and where this guy remains becomes concave. And in the end of the day, F1 in this particular setting is again a concave functional. So the image that I gave earlier, this naive image, still remains true in that setting. Well, never mind. The good news for you today, if you are getting lost, is that I don't need this concavity property today to conclude. This was more to complete the frame. And let's forget for the end of the lecture about concavity, and let's focus on the following important and final step for the variational approach. Namely, weak maximizers turn out to be critical points. What does it mean? The theorem is like this. Assume f lambda is proper. Then, at least we know that it is always the case when lambda is negative. It is always the case when lambda is 0. It is always the case when lambda is positive but small. And it is from time to time the case for lambda positive and large. So assume it is the case. Then the supremum of f lambda on E1 is the same as the supremum of f lambda on the subset E1C for C large. This is by properness. That's my assumption. Now, this is actually a maximum. And this is by upper semi-continuity property of f lambda on E1C. And therefore, this is f lambda of someone. And the claim, or the theorem, is that then phi is a critical point. As I stressed at the beginning of the lecture, if I knew, so with this properness assumption and the upper semi-continuity property and the compactness property of E1C, I have identified one maximizer living in the class E1. If I knew at this stage that actually this maximizer is strictly omega plus monic, then the argument I explained on the first slide would allow me to conclude that phi is critical. But I don't know that. And in general, it will be wrong because I'm solving a Monge-Ampère of phi. I'm trying to solve Monge-Ampère of phi equals mu. And as soon as mu vanishes somewhere, which I certainly want to be the case in applications, then phi cannot be strictly omega plus harmonic. If phi is strictly omega plus harmonic, then the Monge ampere should be in particular strictly positive. Okay? So I need something else, and that's the meaning, the contents of this theorem. Nevertheless, such a maximizer, a weak maximizer, is a critical point. So here is the proof. I consider V an arbitrary test function. You can assume it is smooth, but continuous is more than enough. And consider G of t. This is the following quantity. E composed with P of phi plus TV plus 1 divided by lambda log of the integral of e to the minus lambda phi plus TV d mu. So in other words, I am slightly, G resembles the functional f lambda, but here we replace here phi plus TV by the projection P of phi plus TV, where P of H is the quasi-parasomnic envelope that we have been discussing on a few occasions already. So it's the supremum of those functions W, so that W is omega parasomnic, and W lies below H. And in principle, you should consider the upper semi-continuous regularization. Okay? So the claim that we need some detailed proof, and that will show up in a few minutes, is that G is differentiable and or I should say that maybe it's the key point here. E composed with P is differentiable with E composed with P prime is E prime composed with P. So the projection operator P behaves like a linear operator when composed with the energy function. And as a consequence of that, G is differentiable at 0 with G prime of 0, which is E prime of P of phi plus TV at 0, so P of phi, minus the integral of, sorry, let me phrase it correctly, or more directly, by saying that what you get in the end is integral of V Monge ampere of phi minus the integral of e to the minus lambda phi. So you have a V again, a mu, and you divide by e to the minus lambda phi d mu. Okay? And therefore, phi is a critical point if G prime at 0 is 0. So we have two things to justify in order to conclude. First, that G prime at 0 is 0 whenever G is indeed differentiable. And second, that G is differentiable because E composed with P is differentiable with this nice formula. So let me go on with that. Namely, let me first justify that G prime at 0 is 0. And the reason for that goes like this. I observe that, where am I? So phi is in E1, and V is continuous, hence bounded, and T, say, T moves around 0, okay? I want T close to 0, let's say it's between -1 and 1. This implies that phi plus TV is greater or equal than phi minus a fixed constant C. And this implies that the projection is greater than this projection, but this projection is simply phi minus C, because phi minus C is itself omega prasonic. And this implies that P of phi plus TV is in E1, because phi minus C is in E1. Okay? So I start with phi in E1, as I perturb it in the V direction, and I project onto the set of omega prasonic, and then what I get is a function in E1 again. That's the first observation. And the second observation is simply that P of phi plus TV is less than phi plus TV. And this implies, be careful with signs, that this quantity is less than the corresponding quantity with the projection. So I suggest that you, if you are tired because of the 2 hours of lectures, you do this verification by discussing depending on the sign of lambda. Treat lambda positive, lambda negative, lambda 0 separately, but be confident that this is true. And this implies that G of T is actually less or equal than F lambda composed with the projection. But by the definition, F lambda reaches its maximum at 0.5. So this is less than what you get by looking at G at 0. So if G is differentiable at 0, there is no choice, but G prime at 0 should be 0 because of these inequalities. Okay? So if G is differentiable, then because of this behavior of this local maximum, G prime at 0 should be 0. So let me now, if I go back, what remains to be proved is this claim here. So let me explain the proof of this very important property on the next slide. So the proof goes like this. I want to check that E composed with P of phi plus TV minus E of phi divided by T goes, as T goes to 0, to the integral of V Monge-Ampère of phi. Then let me make a couple of reductions. So changing or replacing V by minus V, it suffices to treat the case when T is positive. Secondly, because E is concave along the Euclidean segments, we know that E of the projection minus, let's say, is less than E of phi plus E prime of phi applied to the projection minus phi. That is to say, you look at E of phi plus the integral of P of phi plus TV minus phi against Monge-Ampère of phi. So this is by concavity. So therefore, you see that the ratio that we are interested in is less or equal than the integral of P of phi plus TV minus phi divided by T mange ampere of phi. But now the projection lies below the function you are projecting. So this is certainly less than the integral of V mange ampere of phi, because P of phi plus TV is less than phi plus TV. Okay, so that gives you one piece of information. Let me now look at the other type of inequality. Again, let me use the fact that E is concave, but with the other point. So what I do get is that E at this point is greater or equal than E of phi plus E prime at the point P of phi plus TV times E of phi plus TV minus 5. Okay, and you can therefore do the same manipulation, and what you end up with is the following piece of information. The only difference is that you're looking at the mange ampere, not at phi, but at the projected point, which is this quantity. Okay, but now let me recall one important property that we have been discussing at length the other day. This is concentrated, this mange ampere measure is concentrated on the contact set, where the projection is equal to phi plus TV. Therefore, this is the same as the integral of V against the mange ampere of the projection. And finally, this guy here uniformly converges as t goes to 0 to V, to phi. Therefore, this converges as t goes to 0 to the integral of V mange ampere of phi. And this is the end of the proof of this beautiful differentiable result. And let me say that, of course, P is Lipschitz, so it's not differentiable, but he behaves, if you like, as we have already seen, like the square of a norm. In dimension 1, I explained you that this is the square of the L2 norm of the gradient. And if you compose appropriately a Lipschitz function with the square of a norm, then you are somehow smoothing out the lack of differentiability of the Lipschitz function, and you end up with something that is differentiable. And then the projection indeed behaves like a linear operator. Okay, so this is it for the variational approach. I think you have the mainstream of this approach, and we have learned how to solve certain important mange ampere equations by the calculus of variation. And again, is that not only is it a way to solve the equation, but it is also a way in practice to understand approximation of the solution. So as soon as you have particular sequences that are more and more maximizing, closer and closer to maximize the functional f lambda, then they will have the tendency to converge toward the unique maximizer in case you have concavity. So we will see, hopefully, in lecture 8, some application of this principle, and perhaps also next week when dealing with the Keller-Ritchie flow, if time permits. Okay, so I'm done with that. I don't know if you have questions or comments.
I have a question. So, as you mentioned in the properness, we can consider not just LP density for the Euclidean volume. So, if we consider non-peripolar measure for the other step, is it still hold?
Now, for the easy case, lambda negative, non-peripolar will do the job. For the intermediate case, lambda equals 0, I need to get, even for the functional to be defined, I need that the measure has this property that E1 is in L1 of mu. So even for that intermediate case, non-peripolar does not suffice. You need stronger information on the measure. And if you pass on to the case lambda positive, then for the measure, for the functional to be defined, you need that exponential of minus certain omega plus monic functions are integrable with respect to the measure. This is a big constraint on the measure. So the measure cannot be simply non-peripolar. It has to be reasonably regular. An example of measures that would work or that could possibly work are measures that are Monge-Ampère of Hölder continuous functions. The corresponding measure may be rather singular. They need not be absolutely continuous with respect to Lebesgue, but they are not so bad in a certain sense. Okay?
Okay.
But a naive question. If you have the properness of the functional for lambda positive but small, which should correspond, say, if you are in the C1 to the solution of the Cantor-Einstein in the Fano case. Is it relevant, or you can rescale the lambda, or where if you rescale the lambda, you can get anything naively. But where am I wrong?
You are wrong in the fact that the upper bound for this positive lambda depends on the homology class of omega.
Okay, I see.
And if you dilate omega because you want to rescale, then
okay, I see.
Dilate also this bound, right?
Yes.
But in any case, there is so for the Kähler-Einstein problem in the Fano setting, even though there might be no Kähler-Einstein metric. So if you normalize things so that Kähler-Einstein will correspond to lambda equals 1, then what this result says is that you can solve maybe the continuity method in order to produce metric with a Ricci constant, which is strictly positive, and then you can go up to a certain level. So this method tells you that there is some uniform control or lower bound on the positivity that you can get, but then there is a geometric meaningful constant, which is the upper bound that you can get that way, and it contains a lot of geometric information. But this method, I'm afraid, will not provide the best positive constant you can get. It simply says there is some uniform positive lower bound.
Okay.
Okay.
Thanks.
Any other question? Okay, then if not, we meet Thursday, but be careful that this is Thursday morning. So this Thursday we meet at 9 a.m. For the lecture, so lectures 7 and 8. And we will finally start considering the Kähler-Einstein problem. So in lecture 7 on Thursday morning, I will give a sort of panoramic view on the Kallenstein problem, both in the smooth classical setting and on mildly singular varieties. And then in lecture 8, I will say a few words about Mabuchi geometry and explain how to use this geometry in order to obtain an analytic criterion to characterize the existence of Kallenstein metric on Fano varieties. So this is the program for Thursday,
Good.
9 a.m.